conceptualize parts per 100. Okay, so let's pretend like conceptualize means try to get a good model in your brain of what it is. Units shouldn't just be little letters that you memorize. Units should have some physical significance. Okay, so the concentration of, let's see which one are we going to do? Let's do the oxygen. It said it was 21 parts per 100. So if you have a beaker of oxygen and it's closed, otherwise it would all escape. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, of course, every model has its limitation. Oh, I can't talk and count at the same time. Let me see. 1, 2, 3. So you draw this along with me. How much do we have there now? 1, 2, 3, 4, 5, 6, 60. Let me see. 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, there you go. There's 100 parts of gas in that particular container. I want to conceptualize 21 parts per 100. So in that container, I'm going to have a total of 100 parts. And of those 100 parts, 21 of them, and I know that I have 10, 10, 21 of them, I'm going to circle 21 of them, would be oxygen. Now, of course, if this were a gas, would these parts be lined up in rows of 10? No, they would not. They would be moving, very quickly in all directions, bouncing off of each other in this container. But for now, we're just trying to conceptualize this business of parts per 100. All right. Now, on that first slide, also with the pie chart, what we say there was 78%, which would be the same as 78 parts per 100 nitrogen. So if I wanted to do that, let me see, 10, 20, 30, 40, 50, 60, 78 is going to bring me up to all of this. That would be my 78 parts per 100 nitrogen, 21 parts per 100 oxygen in air, in a normal air sample. All right, now, what if I wanted to look at carbon dioxide? From the previous slide, it said that we had 0.04% carbon dioxide, which is the same as 0.04 parts per 100 carbon dioxide. So in this drawing, how could I get 0.04 parts per 100 of carbon dioxide? Okay, well, I have 1 part left. All right, so conceptually, that's very difficult if I'm thinking of, breaking my, thinking of 100 parts, and in every 100 parts, 21 of them are oxygen, 78 of them are nitrogen, 0.04 parts are carbon dioxide. So that would be if I were modeling this as a carbon dioxide, I would have to break it up into 100 parts, and take 4 of those parts to get it, to get the fraction of that line that would be the carbon dioxide. But when we're thinking about pure substances such as oxygen, nitrogen, and carbon dioxide, I can't break a carbon dioxide up into smaller bits, because carbon dioxide, as it exists as one bit, does not change. Otherwise, it would change its identity. All right? So that's why sometimes when you're really trying to understand and use this parts per concept to understand units, it's better to express the carbon dioxide in a more meaningful unit, okay? And a more meaningful unit would be parts per million, okay? So a lot of times when we're looking at minor components in a gas mixture, rather than using percentages kind of gives us a global picture. Rather than using percentages, we'll express those parts in units of parts per million, or sometimes parts per billion, depending on the concentration of the substance that is the component of the mixture you're talking about. All right? So mixtures need to be defined by their components and by the relative and the concentrations of the components within that mixture. And the types of units that we choose to use depends on what makes the most sense conceptually and physically.